The question is, in order to stay suspended on this ride, in other words, in order for you to be leaning against the wall and the floor drops out and you still hover, right? The rider must experience a centripetal acceleration of around 2 Gs, okay? According to the ride specs, the Gravitron has a radius of 3 meters. What velocity is required to achieve that acceleration, okay? All right, so just, for funsies, let's draw a free body diagram because you guys know how I feel about them. So here is the circular thing, right? And then everyone, these are all the heads of all the people, right? Here's the heads of them. I'm looking down on it, right? And it's spinning around, let's say, in this direction, right? And so these are all like the little people. And they're all leaning against the wall, right? Okay. And so there is this centrifugal force, which we're going to talk more about the distinction between the centripetal and centrifugal force, right? But it's a pseudo force that creates the illusion that you are being pushed outwards, right? And I'm going to put that in a different color here. Okay, all right? And that centrifugal force, right, that is pushing you against the wall, but every time you're pushing against the surface, you guys know that you have an opposing normal force, right? Okay, and so if here's the wall of this thing and here's the fellow or lady, right, on this ride, okay, if there's a normal force going this way, n, right, then there's also going to be and then there's obviously gravity, weight pushing you down, but there's also going to be then a frictional force here, static friction, right? And that static friction is going to be equal to the coefficient of friction with that wall, mu, times that normal force. Okay? All right? So that's just what's going on. That's how you stay afloat on this guy, right? But what this question is really asking is, what velocity is required to get the 2g acceleration that you need so that you have a strong enough normal force to create that friction that holds you up? Okay? So in other words, my question is, I want to do A equals v squared over r, right? But that A that I want is just going to be 2g. I want that A to be 2g, okay? And we know that g is just 9.8. So that's easy, right? So what velocity is that going to be? Well, that's just going to be v equals the square root of 2gr in this case, right? And what's the radius of this gravitron? 3. So 3 goes in here. What's gravity? 9.8, obviously. And by my calculations, if I put all that in, I get a value of 7.67 meters per second. Okay? So as long as any point on the outside of the cylinder of the UFO or the gravitron ride is spinning at 7.67 meters per second or faster, that should be enough to hold the average person up. Okay? Next question is, at this speed, how long does it take the ride to complete 1 revolution? So this is another way of me sneaking in a period question. How long does it take for 1 revolution? That's just period again. Remember, period is just equal to the distance that you're traveling divided by the velocity. And that's the distance of 1 full revolution, which is just 2 pi r, right? So that's just going to be 2 times pi times 3 divided by the velocity, which is 7.67. So it takes us, according to my calculation, 2.5 seconds to complete 1 full revolution then. Okay? So this is what you can tell your friends next time you're at the carnival and you're actually staying up. You can completely describe the mathematics and the physics and the free body diagram for why you don't plummet to your death when that little guy falls away. And that's how powerful physics is, okay? Because you actually survive because of it. I think that's pretty neat. If you guys could advance to the next slide, we have a misconception question. And it says, which of the following point towards the center of a circle in uniform circular motion? The acceleration, A. B, the velocity, acceleration, and net force. C, the velocity and acceleration. Or D, the acceleration and net force. Well, we know that acceleration is always pointing inwards, right? acceleration, 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 right? And we also know that F equals ma, right? So that force is always pointing in the same direction as acceleration, right? If an F vector equals m times an a vector, right, that mass doesn't change anything. So whatever direction that acceleration is pointing, the force that's caused by that acceleration, or the force that's causing that acceleration, must be in the same exact direction as it, okay? And in this case, this force causing that acceleration is the normal force, okay? And I know that might sound tricky, and we're going to explore this a little bit more, but the only thing keeping you in circular motion here is the normal force, is the force of the back of that wall. You take that wall away, you fly away, right? That normal force is what's creating the acceleration that keeps you in uniform circular motion, okay? Ponder that, and I'll see you in the next video.